In solving induction problems, there's a lot going on. The coil's got to be described, the change has to be described. Usually we're asked for a voltage, but maybe I could switch it around and ask you, maybe give you the voltage and ask for something else. For this particular one, when I set it up, I'm going to start off with, I think, the most confusing part, and that's the angle. This one says that initially the coils are perpendicular to the field, but then they're rotated 90 degrees. So what I mean by that is imagine we've got a coil. It doesn't give the orientation, so I'm just drawing it a way that my brain kind of visualized it. If you visualized it different, you might not be wrong, just this is the way my brain sees it. It says that the loops are perpendicular to the field, but it didn't give us much else. So perpendicular to the field means this sort of orientation that I've drawn. The loops are kind of in the up-down direction, and the magnetic field lines is in kind of the left-right direction. In a situation like that, even though the word perpendicular is in there, really what that means is that the angle between the coil, oops, not cosine, the angle between the coil and the magnetic field is 0 degrees. Remember, we always talk about the direction of the coil as the normal. So the normal would be pointed kind of left-right. The magnetic field lines are also pointed left-right, so we could call that an angle of 0 or even an angle of 180. Questions like this are often vague, and it's going to lead to maybe differences in the end of a question. Someone might say positive voltage and someone else might say negative voltage. To narrow down the direction of voltage or the sign of the voltage, we need to have a lot more words. So if it's just vaguely worded like this, then we can just roll through and just sort of put in numbers as we interpret them. We should agree on the number we get for voltage, but we may disagree on the sign depending on our interpretation, and that's okay. Our driving equation where we're trying to determine a induced voltage is the change in the magnetic flux divided by time. Magnetic flux is this weird combination of the magnetic field, the number and area of loops, and the cosine of the angle between the loops and the field, and how quickly that changes. In this particular question, the number of loops isn't changing, the size or radius of the loops isn't changing, the magnetic field isn't changing. So in this particular question, we can kind of factor those things out of the delta. So the B and A can come out of the delta. Really, we've got delta of the cosine of x. Delta is always second minus first, so really this turns into B and A cosine of the second angle, take away cosine of the first angle. And then all of that divided by t. If we scroll up so you can look at the numbers, 100 loops, that's our n. It's a circle, so when we plug in area, the area of a circle is pi r squared. Now we'll have to convert the 4 to meters. The b value is given as 0.5. It goes from whatever angle we start off with to 90 degrees more in 0.1 seconds. Again, it's kind of vague, so we might disagree on the sign, and that's okay. When I plug in numbers the way I'm seeing it, the b was 0.5. The n was 100 loops. The area is pi r squared. The r was 0.04. When we put it in meters, we have to square that. The way I've set it up, the first angle was the 0 degrees, and it rotated 90 from there. So the second angle is 90 minus the cosine of the first angle. And all of that mess happened in a time of 0.1 seconds. Interpreting it that way, I get a voltage. The value is 2.5 volts. The way I interpreted the angle, I got a negative. I'm okay if you say positive 2.5. Really what the sign on the voltage does is it communicates which way the electricity would flow in the wire, which way the electrons would get pushed. Usually we don't care. Just the voltage tells us how hard they're pushed. Maybe we would do other engineering off of that. So don't get too worked up about the sign, but you should be